Hello, Doctor. My name is Braden Lee Ting Feng from Section 2. So, for our computer organizations and architecture group project, I will be the one who doing and demonstrating TOE3, which is the PassMark performance test. So, basically, PassMark performance test is a benchmarking tool that allows us to conduct component level standard scoring. So for this project, we are just focusing purely on CPU microarchitecture. So as you can see on the main dashboard, by navigating CPU marks, the pass mark break down into specific subtests like integer mat, floating point mat, extended instructions, and sorting. So this modular design is highly beneficial because it allows us to isolate specific workload rather than just getting an overall generalized scope. Right, so first of all, let's look at the workload A. So basically, the objective here is to capture our code pipeline processing throughput. So in order to do this, I need to execute the standard CPU instructions, specifically the integer mat, floating point mat, and sorting mat. I mean sorting algorithm, sorry. So let's run it one by one. Right, so we are running for the integer mat now. Floating point done. And finally, we have sorting. Right, so once the test finish, let's look at uh, the text right inside the tile, which is here. And uh, this is the graph of it. So to find our computer organizations and architecture metrics known as MIPS, or million instructions per second, we apply a mathematical transformations. So we take this uh, row operations per second score and divide it by 10 to the power of 6. And yeah, so this gives us a direct measure of our CPU pipeline saturation efficiency. So same goes to the floating point mat and sorting. Right, so now let's transition to workload B. So basically, this workload evaluates the advanced architecture behaviors, specifically focusing on single instructions, multiple data or SIMD vector units, and a floating point unit throughput. So to do this properly, we must isolate our testing. So I'm executing only the floating point mat and vector mat portions of the sub. So this forced my 11 Gen Intel Core i5 processor to heavily engage its advanced architectural extensions like AVX2 and AVX 512. Right, so now we run for the extended instructions first. And for the floating point map. Right, so now it is finished, and we need to extract our GPLOPS rating. So as you can see on the horizontal axis here, so the pass mark measures this specific test in millions metrics per seconds. So my Intel Core i5 achieved a score of um, 70,000, I mean 7,898 millions metrics per seconds. So to convert this to GPLPS, which stands for Giga floating point operations per second, I divide it by 1000. So this results in a SIMD efficiency of uh, 7.898 GFLOPS. So yeah, so to conclude with my analysis, the floating point unit of this CPU achieve a converted throughput of which is here 16.718 GFLOPS, while the vector heavy extended instructions achieve of 7.898 GFLOPS. So the SIMD pipeline is highly efficient because it processes multiple data points simultaneously using wide data path in a single instruction cycle. So, however, it is important to note limitations of this tool. So, for the PassMark, it runs this vector test in very short, synthetic bursts. In real-world scenarios, heavy AVX vector instructions generate massive amount of heat. Because these tests are so brief, so they do not accurately reflect the thermal throttling and clock speed degradations that our CPU would experience during a substantial real-world workload. Yeah, so thank you. That is the conclusions for my demonstrations for Tool 3.